Hello, I hope all of you are doing fine. Now, in the last few sessions, we have understood in dynamics that we have understood really that there are certain dynamic forces which are generated in the system when the mechanical system is working, and at times these forces are disturbing and fluctuating. So there is a need to control all these forces which are coming during the operation of the mechanical system, and for which even we have tried to control them with the help of maybe by understanding how these are coming into the system. So one reason we have understood that this might be due to the unbalance which is created in the system. So we try to balance those masses because there are various masses moving in the system, mechanical system. So we have tried to control all these with the help of balancing the system. Objective was ultimately to have a smooth operation of the system. Then we have understood these inertia forces which are coming, not only these inertia forces, but other than that there is as well like fluctuation of the energy also in the system. So maybe with the help of the flywheels we have tried to smoothen out these fluctuations, because ultimately this fluctuation in the energy is also affecting into the fluctuation in speed, which is again creating disturbance or non-smooth working of the mechanical system. Then operational conditions also can be disturbing. So we have governors to control those speed or operational conditions which is varying due to the variation in the load on the mechanical system. So these are the things we have seen, and every time we have been trying to make our system a smooth functioning or smooth working system. But still as well we have understood that we cannot completely make them free from these disturbing forces which are also again time varying. So these are fluctuating and these are very much disturbing in the system. So what happens due to these forces in the system is that like every mechanical system, if we see, it will be having some equilibrium or a stable position or an equilibrium position, right? So what is happening due to these disturbing forces is these forces are moving this our mechanical system from its equilibrium position. So it is moving it away from the equilibrium position, and thus again the system is trying to, or it has a tendency to again come back to this equilibrium position. So this is creating fluctuating, you can say, motion, or this is causing an fluctuating oscillatory motion, right, which is disturbing of this entire system. And this fluctuating oscillatory movement is called as the vibration. Right, so what we are trying to understand here is vibration in mechanical systems, right? So now these is definitely causing a problem. Now there is, then again I can put a question, why there is need of understanding vibration. Now as we are saying at times this is causing a disturbance in the system, or it is affecting into the smooth functioning or smooth working or smooth operation of the system. So hence, until and unless we understand what this is or how exactly the behavior or the phenomena this is, then we won't be able to control this vibration. So until and unless we understand this, we cannot control it. Now then the question can be, why to control it? Why not let it be there? Now if it stays there, then it is definitely going to affect the components involved in the mechanical system, because we can see, or we will see when we will be studying, it will be increasing the stress level conditions in the components which are there in the mechanical system. So hence we need to control this. Then another aspect can be, not only we have to control, so to control I have to understand, again to utilize also, for its utilization, because there are so many mechanical systems or machineries wherein we are utilizing vibration. So for instance, or for example, the mechanical compactors, compactor machines, if you see, they are vibratory compacting machines. So due to this vibrating forces, nowadays we see the compactors are quite lighter as compared to earlier compactors or road rollers for that matter, if you see, because there we are utilizing this vibration, which is really creating such dynamic forces during the operation. So that is why I can say, or we can say, that we need to understand, first we should be in a position to control where it is not required, and secondly I am in a position to utilize that. So that is why I can say that we need to understand or what vibration is. Now before getting into or deeper into what vibration is, let us try to understand or this vibration in a overall view. If we see how this can be categorized, or in a way what are the various types of types in which we can categorize this vibration. So first thing we can say, so vibration, so first category I can say that this can be classified in a way based on maybe vibration based on the energy source. Right? So according to this we can say free vibration, forced vibration, then self excited vibrations, and parametrically excited vibration. So this we can say, or I am saying that this is based on the energy source. Energy source means how this disturbance is actuated in the system. Like free vibration, if we see, in free vibration the actuation is due to application of a disturbing force just once. So just like if I tap, for example, if you see this as let us say call this as a beam, and there is application of this force, and you will see that it starts vibrating. So there is application of this force just once, and this system starts vibrating. So that will be called as a free vibration. Now forced vibration, I can say that when there is a continuous application of a disturbing force, and which is a periodic disturbing force which is coming into the system, right? So these two can be categorized. This is the free vibration, where only once, so once the once the system is disturbed, you can say, so the vibration is there in the system. And then in case of forced vibration, so there is a application of maybe a periodic disturbing or continuous disturbing force in the system, right? So that is why the system is vibrating. Then self-excited can be the example wherein there is no external force or external disturbance which is creating that vibration or the oscillatory motion of the system, like our vocal cord when we are talking. So it is self-excited, it is generated that way, the vibration is created and the sound is created. And parametrically vibrating or excited system are more or less same as that of a self-excited system. So we can say this is one category or one way by which we can classify the vibration. So based on energy sources, you can say. Then second, I can classify this maybe I can classify the vibration by based on maybe the based on motion, you can say, the motion of the body, based on motion. So here we can categorize this into as longitudinal vibration, then transverse vibration, and torsional vibration. Now by based on motion we mean when the disturbance is created, so obviously the body is moving about the mean point. Now this movement or the motion of this body, if it is along the longitudinal axis or the longitudinal axis of the system, then we are calling it to be as the longitudinal vibration. And like if this is a system and disturbance is created, so this is the longitudinal axis and the system vibrates along the same longitudinal axis, so we will be calling it as longitudinal vibration. Whereas now if I create a disturbance this way, so the body is moving perpendicular to the longitudinal axis, so then it will be called as a transverse vibration. So let us say if there is this kind of a body and this is some mass, so I tap it, so you will see that this system is vibrating along the longitudinal axis. Whereas in case of a transverse vibration, if I tap it this way, so this is going to vibrate in this direction, right? So when the movement or motion of this particles of the system, if it is perpendicular to the longitudinal axis, then we will call it as a transverse vibration. And the third, torsional, by this we mean when the motion of the body due to disturbance is about an axis or about the longitudinal axis. So kind of you can say the rotational vibration, if it is there, so that is categorized as, or that is understood as, a torsional vibration. Now the third classification we can say can be based on nature of dissipation, right? So nature of dissipation. Now the body is moving, so there is some kinetic energy, the energy is there in the system. Now this energy is utilized and dissipated in the environment. So based on how this is getting dissipated in the system, we can categorize that as, first, as a undamped vibration and damped vibration. So undamped, this we can say that there is conservation of energy. So energy is getting transformed from one form to other form and it is conserved in the system. So there is no kind of, theoretically there is no dissipation. So we can say the vibration is continuous. So it is there in the system. Whereas in case of a damped vibration, so what we are doing is we are dissipating that energy with the help of, so in this case you can say this vibration is dying out due to as this energy is getting dissipated or consumed by some other mean in the system, and we provide damping as viscous damping, then Coulomb's damping, viscous damping, Coulomb's damping, and material damping. So where viscous damping means where a fluid is utilized to absorb that energy from the system. So kind of maybe some fluid or oil is used. Coulomb means it is with the help of the energy is dissipated with the help of friction. So this is dry friction, you can say. And material damping means due to the internal frictions and all, so this energy is lost in form of heat or sound. So in form of heat or sound, when this energy is dissipated in the environment, so that is called as material damping. So this is one of the broader classifications, again we can say, for vibration. Now there is another classification or type, we can say as, okay, fine. So this is number 2, this is 3, so I take 4 here, based on, I can say, based on nature of you can say nature of the system, based on the system, or maybe you can say the complexity complexity of the system. So that can be classified as, say, single degree of freedom system. That means a single variable is able to explain the equation of motion for that system. Then can be multi degree of freedom system. So there is more than one variable with the help of which we are able to express the equation of motion of the system. And the third can be infinite degree of freedom system. So where infinite variables are involved to express the equation of motion. So in infinite, basically then we disintegrate the system into multi-degree and all. Likewise so infinite degree of freedom can be, we can say, the movement of an elastic body. So the motion of an elastic body, if you imagine, it will be having an infinite degree of freedom of movement in the system. So this is the next way we can express. Then finally there is, so this fifth category, I can say, this is based on, again this is based on the nature of the motion, rather it is based, here we have seen motion, so I will say based on now not only the motion but based on the nature of the motion. So this we can say can be harmonic. The displacement or motion is harmonic. That means the displacement or equation of motion is a sine function or a cosine function. So it will be harmonic and periodic as well. But say second is periodic, but it is anharmonic. So it is periodic, but so if you see this is a sine or a cosine. The equation of motion you will see will be a sine or a cosine function. But here for periodic but anharmonic motion, so if we see the motion, so maybe it is periodic. You can see it is, the motion is periodic, but it is not a harmonic one. So this can be one case. Then third is random. So here the motion is just random. You cannot equation of the motion, if you see, it is random vibration. So we are not able to express or understand that. And finally it can be chaotic. So it's just chaotic. So we are unable to understand how the motion is. So that is how, in a broader way, we can say this can be a basic classification or a bird's eye view. Okay, fine. There is another one classification remains there. We can say, so let this be the sixth one. Classification of the vibration can be linear and non-linear. So we see that the functions, the disturbances, they are linear or non-linear as well. So this can be also so that is how this is a kind of a bird's eye view of how vibration can be classified. into various types in a way. So now we can move ahead to understand what exactly now the vibration is. So before that, we then need to understand what are the various parameters of a vibrating system, right? So let me just first clean this board. So let us try to understand that what are the, we can say, the basic elements of a vibrating system. Now, it is very important that a system must have a stable equilibrium position, right? And when it is so, then it must come back to its stable position. So, say for example, say this is a mechanical system or a body, and it has its stable, it is its equilibrium position, or you can say the stable position. Now, due to some of these disturbing forces in the system, what is happening is the body is displaced from its stable position. So, let us say it is moved, say to the left, to the right, fine. So, this body is moved with the help of some disturbing forces. So, it has been displaced to say this position 2. Now, if say there is a body on a plane surface and I disturb it, so I give it a displacement, so it moves and stays there, right? So, it is not coming back, so I cannot call that as its stable position, right? So, if it is a flat surface and if I move it or if I displace it, it will just go and maybe stop there, or it will continue to move ahead. But now if I say, if I make it a curved one, like in this case, if you see, so if I displace it, so it is coming back, right? So now why it is coming back? It is due to the nature of this system, right? So as I am providing a curve, so gravity is helping it to come back to its stable position again. So this, when this is taking place, so when this body is having a tendency or having a capacity to come back to its stable position, now this is called as restoration. Right, so it will have restoration. So this is must. So to identify a system as a vibrating system, then certainly it will be having a restoring capacity. Now this can be due to anything, any parameter which is there in the system. Like I have quoted the example here. So if it is, say, if we take a bowl, right, and there is a ball, so if I push it, so it will move. Now due to gravity it will come back. So the gravity is providing the restoration in this case. right? Or maybe it can be the stiffness of any body, the elastic property of the body, which will be restoring it. So like in this scale, if you see, when I bend it and I just release it, so it is coming back due to the elastic property or its material property, it is coming. So this is restoration is taking place. Now what is happening is, so when this body is restored, so it is approaching its stable position, but what is happening in this case is the body, as when this is moving, it is a non-zero velocity, then definitely this body will have some inertia. So due to this restoring force, this body is moving towards the stable or the equilibrium position. But as this velocity condition is a non-zero velocity condition, so the body will have some inertia. Right? Now due to this inertia, what is happening is, as the body approaches the mean position, but it has acquired some inertia, so it is not going to stay at this equilibrium position, rather it will overshoot. So this is going to overshoot from the equilibrium position or the mean position. So from say 1 to it has reached to 2 and it is restored to reach 1, and again it will, so due to this inertia, it is going to overshoot this stable position and it will move ahead. So thus when it moves ahead, so again due to restoration, it will be pulled back to its original position. So again this inertia is going to play the role. So these two things are definitely going to be there. So what we can say as the parameters of a vibrating system, so first definitely it must have it will have inertia, of course restoration capacity, and there is a third element here in to identify mechanical vibrating system. It is the dissipation. So dissipation of this energy, though I can say that this dissipation is not necessary for the body to vibrate, but certainly it is present all the time in a system, maybe in the form of, like if we see this example of a pendulum, say this is the mean position, say, and so it is displaced by theta. So when we say this, so this mass is acting this way, so due to this gravity, restoration is taking place, right? And as it is having some mass and it will be having a non-zero velocity, so it will have some inertia, so it will come to this position and it will overshoot the mean position, and that is how we can say the pendulum it is vibrating, or vibration is taking place here. Now if we take we see that if we consider this as to be a massless pendulum, then in that case inertia will not be there, right? So though it is having restoration, so maybe when we are displacing it by theta, when we release it, so it will be restored, but it will not overshoot the stable position, rather it will come back to its stable position and will get stable. So that is how we can say these are the three most important, or this is how we can identify a system, a mechanical system, to be a vibrating system, when we identify that it is having these three elements, these three parameters in the system, that is inertia. System is having some restoration capacity, and as well maybe there is dissipation. Like here you can say I am not providing any external damper in the system, but this dissipation will take place maybe due to the friction with the air. So for overcoming that friction with the air, maybe friction at this pivot joint what we have provided, so these the energy is getting dissipated through these places, you can say. And so dissipation will be definitely present all the time in any vibrating system. So that is how we understand. Now if we see, say there is any mechanical system, right? So say maybe there is some mechanical system, right? Now say I am applying some force, right, here, or better way if we understand it, try to understand it this way. Say this is a beam and there is some mass attached at the end of this cantilever. Now to solve such physical systems, in engineering we have seen, what we are always doing is we are converting these like if I say this is a physical system, right? So we are converting those physical system into mathematical models, right? And then we are solving these mathematical models as as we write those mathematical models as some equations, and we solve the equations to find out the solution for the system, right? So to convert these physical systems into mathematical modeling, so in vibration definitely we are not solving the exact physical system, we are converting them into mathematical models, and then we are finding out the solutions for them. So what we do is we do the, what you can say is lumping of parameters. Right, so we are lumping these parameters. So what that means, that is how we are converting this physical system into a mathematical model. So say if this is having some mass m, right, so and say some force is applied, so this starts vibrating. Now if you see the actual system, this is having a mass, so entire body is having some mass, so every particle of the mass is having inertia, right? So due to this mass definitely there will be inertia. So as we know, this inertia is, magnitude of inertia is force is equal to that force, so minus mass into acceleration I can say. So what we are doing is, so inertia in the system is provided by this mass. Now when say I am applying a force in this direction, so this is getting bent, so this beam is providing the restoration, right? So the restoration is provided by this beam. So that means this will be due to whatever stiffness, you can say, stiffness of this material of the beam, or this is provided by this beam. So how I am converting this system, and maybe say the air resistance, or there is some other component by where the dissipation is taking place. So if anything is not present, so maybe the internal resistance, internal friction of the particles, the air present, surrounding it. These are providing that restriction to the motion, so the energy is getting dissipated through this. So dissipation is there. So how I am converting this system, maybe you can say, so there is this one mass which is there, and when it is getting displaced, it has been restored by spring by some stiffness K, and the dissipation is done through some equivalent I can say where we are damping the system. So that is how we have lumped all those parameters. So in lumping we can say the inertia we have mass, right? So it can have a linear motion, right? Or it will be I for component or parameter which is representing, you can say, inertia, will be the mass. M if the motion is linear. If the motion is rotary, then in that case the inertia element will be represented by the mass moment of inertia of that body rotating about that axis. Then second element we have seen is the restoration. So restoration is done by what? The stiffness present in the system. So we can say it is represented by the spring stiffness, which is denoted by K. If it is linear, if it is rotational, so torsional, it is represented by Q or capital K in some. So this will be the restoration, can be through stiffness, maybe linear spring or coil spring. On third restoration, as in case of pendulum also we have seen, so the third can be, maybe if this is the case, so we can say it is the gravity G. So restoration can be as well provided by gravity. So the inertia is represented by the mass or mass moment of inertia. Restoration is represented by the stiffness in knee form, we can say, and third is the dissipation. So dissipation is done by the damper. So we are considering here, or we are taking it or converting into an equivalent viscous damping condition, so that is represented by the damper, right? So with damping coefficient C. So these are actually, say, if I am pulling it, so there are holes and it is filled with fluid, so fluid rushes from this side to this side. So that is how a resistance is provided. That equivalence we are taking. So this is how we represent a viscous damper, and there can be dry Coulomb friction in that case. So if this is the force, so we represent it by this symbol. So the coefficient of friction, so he is going to give us the dissipation. So that is how the dissipation will take place in the system, right? So that is how we can say we can lump the system in this fashion, or we can say this is how we identify the basic elements in a vibrating system, right? So that is how we have identified these basic elements of a vibrating system as inertia, restoration and dissipation. Now before I stop the discussion for today, let us also talk, like here I have discussed, say there is, say here, say I am ignoring the dissipation component here. So say a free vibration we'll call, or undamped vibration if I call this, so having stiffness K. So here there is only one variable by which I can explain, that is the displacement of this body, say x, right. So there is only one parameter, so this is going to express x dot, x double dot. So this is having only, with the help of one parameter I can express the equation of, or with the help of only one variable I am able to express the equation of motion for this system. Or for example, say, so if this is a pendulum, so here just with the help of theta I am able to express the displacement of this body, so, or the equation of the motion. So I will call this as a single degree of freedom system, where I need only one variable, maybe in this case theta, in this case x, and I am able to express the equation of motion. So similarly, if I see a system like, say, where this is, say, mass m, and say this is m1, so this is k and this is k1. So here you may say that x1 and x2, these are the two variables required to express the displacement, right. Or here for a pendulum case, if you see, so maybe it's a double pendulum, so this is theta 1 and this is some value theta 2. So we need to express this with the help of two variables. So this will be a 2 degree of freedom system. Now if you really want to understand a physical system for this, so for this I can say, if say this is a comparison, say maybe there is this beam, to its end there is a considerable mass which is placed there and this is getting displaced. So if I compare the magnitude of, or the distribution of this mass compared to this mass, so as if I can say that the entire mass is kind of concentrated at this end, so only the stiffness is provided by this particular small strip of beam. So that complete entire stiffness I am considering for is provided, or the restoration is provided by this beam. But now if I say a system is say it is a continuous beam like this, right. So here I am unable to represent it with the help of a single degree of freedom system, because this entire mass is considerably distributed. So what we are doing in this case is, then I am converting this system, this entire system, into maybe as this, and then with same as, say, this. So effect in this is same as that effect in this. So that means I have converted this system into a 2 degree of freedom system. So likewise, we understand what the physical system is, and based on which we convert it into a mathematical model and we try to solve this equation. Now here, as I have separated or disintegrated this entire beam into two, so I am getting a 2 degree of freedom system. I can divide this into more number of parts as well. So maybe I divide it into these many parts. So if I do so, so maybe I have a system So maybe then it will be a multi-degree of freedom system. So then I'll be solving that equation. Of course, the more number of elements I take, the accurate my answer will be. So that is how our approach will be to understand given mechanical system, to convert it into mathematical model, and to determine the equation of motion and the natural frequency and all those things involved in the vibration. So that's all in this session. So in the next session we will move on to how to get those equation of motion for the vibrating systems.